The next presentation is by Vladimir or even Korviakov, Moscow Research Center of Huawei, and the topic of his presentation is ISyNet's design of Pareto-optimal neural architecture for computer vision task on neural processors. Vladimir. Hello, friends. I hope you can hear me well. As it was said, the topic of my presentation is ISyNet. ISyNet is the name of our laboratory, Intelligence Systems and Data Science, and I'm head of the group on neurals algorithm. So the backbone in computer vision and deep learning is the neural net architecture that takes feature from source input data, and they are produced by the so-called heads trained to do specific tasks. Each of them is trained for a certain. So here you see the simplified architecture of a model to solve a task of car brand recognition. The backbone takes features from the input image of a car, and the heads would identify brands, color, year of manufacturing. Why do we need good heads and backbones? They allow researchers and engineers to allow two goals: to get a model of a better quality. What's important, the data set of our target task, if it's not that big, you can train the model quicker. At the moment, the most popular backbones are VGG, ResNet, MobileNet, EfficientNet, Vision and Transformer, the new class, and so on. Why do we need special backbone for hardware? So you see a screenshot with the current leaders, the leaderboard of VisionNet, the data set used for preliminary training of backbones. And you see that for many years, among researchers, it was important to get the model of highest quality, even if the complexity was high. And you see that they have 2.5 billion parameters, which is absolutely impractical for application models. And the metrics of complexity, flops, max, parameters number are too abstract to make a decision when you mean working on specific hardware. That's why, for practical applications, it makes sense to develop special backbones, customize for specific hardware. And you need to provide research and users not just one model, but rather a family of models that would keep them satisfied with the quality of work. So as for the hardware, devices from AIJ family neural processing unit based on Da Vinci architecture, and you can divide them into two branches. Ascent 310, Inference Accelerator Atlas 200 AI model, Edge Station Atlas 300i card, Atlas 500 AI Edge Station, and Atlas 800 inferencing. And for training, among training accelerators, you have AISyNet 910, Atlas 300T card, Atlas 800 training server, and Atlas 900 AI cluster. You have the link here. What's Da Vinci architecture? All these devices are based on. The architecture computing core is shown here on the graph. The main modules include cube that performs multiplications of two FP16 matrices, 16 by 16 or 16 by 31, with int A accuracy. And operations include convolutions and fully connected operations. The second most important part of the architecture is vector unit that actualize operations within activations or batch norms, elements, norms, addition, and so on. The third unit is Scholar unit, and there are non-computing units like a number of buffers, L2, L1, L0 unified buffer. They have different sizes. They are connected by different channels and throughput. And the last important element is the so-called memory transfer engine, MTE, that manages read and write operations between different buffers. And apart from that, performs operations like padding, transposition, and IMG2 call. And what operations are the most time-consuming for neurals? There are three main operations: matrix operations, as I told you, vector operations, and another important component is operations with the data, their transfer, transform and formats. It also contributes to this. Based on what I said, what properties fast architecture for Da Vinci platform should have? Ideally, the shapes of all tangents should be divided by 16 or 32, depending on the accuracy. You need to prefer matrix operations over vector operations, and the higher is cube utilization, the better. There is an exception: operator fusion mechanisms that allows to efficiently do it if there is a sequence of operations matrix to vector. Then such sequences are carried out efficiently, and you can lead them to batch norm activation. Well, again, it's important to avoid redundant data copying. When possibly, you should avoid element-wise operations like summing, multiplications, and data permutation. You should avoid branched architectures, but two chain-like architectures. And also, you should prefer lightweight activation, like reload, compared to swish, mesh, GU, and so on. And of course, there can be exceptions from every one of these rules, but you need to realize when an exception, a violation of the rules, offers more advantages. Based on that, we developed the search space and the neural architecture search algorithm. So it's worked with data sets. So it included the architecture itself with its latency on hardware and quality obtained following a simple procedure. And we trained two models, surrogate models, and then we data sampled the architecture, trained them with the help of those surrogate models, and then we replenished the data set and repeated the process a number of times. And we had the front data set, and then using this architecture, then we scaled it, and then we improved training procedure, getting the best possible quality. As for the scaling procedure, at first we used existing procedures as compound scaling. If you remember ISyNet article, but this method is focused on scaling by doubling flops number for the model. And as we found out, this number doesn't fully correlate with the time of processing on a hardware, and we developed our own simple but efficient algorithm which do the scaling just to obtain an architecture A2 with a certain latency from the architecture A1 that allowed us to scale the depth. And the practice showed that this method was efficient, and it was proved by experiments, as you see on the graph. You see our results on this slide, and you see that our models in terms of Pareto index are better than ResNet models, and ResNet models were trained with our best training procedure, so the comparison is honest. So why ResNet? There are two main reasons. Because ResNet are reliable working horses. Everyone knows them. They are used frequently. And the very architecture of Da Vinci was designed for ResNet. And ResNet models are quite good. So if we could develop a better model, then it's really efficient. The way they work is shown at the right. You see the classical multi-stage structure with the space going down, tensors going up. Depth, we don't always use skip connection due to the requirement that you should avoid element-wise operations. And you see that the algorithm found exciting construction like decomposing 41-3. This is a slide about transfer learning. And researchers forget about it in their new publications. They normally cover ImageNet. But it's even more important that the models be applicable for some practical tasks, and we reviewed 9 target models, and again you can see that in most points our models outperform the best ResNets we could obtain, and we can arrive at a conclusion that our models would be good for real scenarios in the area of computer vision. We also plan to share our code at work and mine Spore Model Zoo. I hope it happens before the end of the year. So this model zoo is available at the link on the slide. And I would like to thank all the researchers who were involved in developing the architectures for their work. And you can get the details from this article. You see the link on the slide. Thanks so much for your attention, and I hope I still have some time for your questions. Vladimir, thanks a lot. Sadly, there is no question for you from our users, but I would like to ask a question for myself. What are your plans for the next 2 years to develop this Da Vinci architecture? So where do you invest your time for the future? So we actually work on architectural issues. We don't design the hardware itself. We plan to look, and we are researching the possibility of deploying more powerful models like transformers, vision transformers model. And there are architectures popping up every week. And we plan to find an architecture that would be efficient for our hardware. And so that's the trend for our future development. Clear. Vladimir, thank you very much.